we studied about the nomenclature of carboxylic acids. So if you take acid chlorides, when it undergoes hydrolysis, what will happen? C6H5COOH will be formed. In the presence of a base, first what happens here is OH and Na. Vinegar is nothing but dilute acetic acid. It has got a pungent odor, no? Hello my dear students, welcome back to session 7 on the chapter Aldehydes, Ketones and Carboxylic acids. Last class we studied about the nomenclature of carboxylic acids and also some of the methods of preparation. Some more methods of preparation are there which we are going to learn today. Okay. So first is from Grignard reagent. So from Grignard reagent, how can we prepare carboxylic acids? That is, you take Grignard reagent, it reacts with carbon dioxide, that is CO2, okay, or dry ice we can tell. In the presence of dry ether, it will form a compound in which CO group is getting added to R group and MgX is getting added to one of the oxygen atoms with the negative charge. Okay, so it forms a carboxylic acid salt, I can tell, which on hydrolysis in the presence of a small amount of a mineral acid, you are going to get carboxylic acid. That is here H and OH will get added up. Okay, we shall write an example for this. R, I am going to take it as CH3 group, MgCl plus C double bond O, that is carbon dioxide or dry ice. In the presence of dry ether, when it is heated, we are going to get CH3, C double bond O, MgCl, that's O minus, and this is plus, which on further hydrolysis, you are going to get CH3COOH, that is acetic acid. Okay. So this is how we write the example. Next method of preparation is from acyl halides. So if you take acid chlorides, when it undergoes hydrolysis with water, see with water when it undergoes hydrolysis, you will get carboxylic acids, or it can undergo hydrolysis with aqueous base to give carboxylate ion, which on acidification will give carboxylic acid. So understand, if I take acid chloride RCOCl, if I add only water, then what happens is we will get RCOOH and Cl minus is removed. It can also undergo hydrolysis in the presence of a base, okay? Then you will get carboxylate ion and Cl minus, RCOO minus and Cl minus, which again has to be acidified to get carboxylic acid. Okay, so we'll write an example for this. CH3COCl with water, it can form CH3COOH plus Cl minus. Okay, so this is acetic acid. In case we use aqueous solution of a base, then you will get CH3COO minus and Cl minus. Further, it has to be acidified again to get CH3COOH, that is acetic acid. Okay. So I hope you have understood and you all are writing the reactions as I am writing here, or at least you can pause the video. Once you watch, you understand, please write down the equations and learn. Otherwise, you will find it difficult to memorize later. Okay. So we'll go to the next method of preparation, that is again from acyl anhydride. So if we take an acid anhydride, for example, if we take benzoic anhydride, C6H5CO twice O, this on hydrolysis, it will give benzoic acid just with water. Okay. What will happen? C6H5COOH will be formed. Two molecules of benzoic acid is formed. Now, for example, you are using, benzoic ethanoic anhydride. You have C6H5CO and CH3COO group. Okay. Now this one, if you add water, then two different molecules you will get. That is, you imagine here H and OH is getting added up. So you will get C6H5COOH, benzoic acid, CH3COOH, ethanoic acid. So two different types of acid you will get. This is from acid anhydrides. Next is from esters. If we take ester and if it undergoes acid hydrolysis, you can get carboxylic acid directly. Otherwise, you have to take ester and in the presence of a base, it will give a carboxylate ion, okay, which on acidification will give you the carboxylic acid. For example, we'll take ethyl benzoate. You have the benzene ring with C2H5COO group. In the presence of water on hydrolysis, it will give, here you can see H and OH will get added up. You will get benzoic acid, COOH, it is with the benzene ring, and C2H5OH and alcohol we will get. Similarly, if I take ethyl butanoate, this is the ethyl group, this is the butanoate group, 1, 2, 3, 4, 4 carbon atoms, okay. In the presence of a base, first what happens here is OH and Na will get added up. So you'll get a sodium salt of a carboxylic acid or a carboxylate ion with the sodium ion you will get, and an alcohol is formed. Now this sodium salt of carboxylic acid on acid hydrolysis, again sodium will be replaced with hydrogen and you will get the carboxylic acid, and in this case it is butanoic acid which we have got. Okay. So I hope you have understood this particular method. Next is the physical properties. What about the physical properties? Aliphatic carboxylic acids up to 9 carbon atoms are colorless and liquid in room temperature with unpleasant odor. For example, if you would have smelled vinegar at home, okay, vinegar is nothing but dilute acetic acid. It has got a pungent odor, no? It has got just 2 carbon atoms chain in that. It's up to 9 carbon atoms. They all are liquid at room temperature, but they have got a pungent, unpleasant odor, okay. The higher acids are wax-like solids and are practically odorless due to their low volatility. Okay. Next, carboxylic acids are having higher boiling point compared to that of aldehydes, ketones as well as alcohol of similar molecular mass. What is it? Carboxylic acids have a higher boiling point compared to that of aldehydes, ketones and alcohols of similar molecular mass. Why? This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. So within the molecules of carboxylic acid, there is hydrogen bond present. You can see here RCOOH, RCOOH. Between the oxygen and the hydrogen of two different carboxylic acid, there is a carboxylic hydrogen bond. Here there is one more hydrogen bond and they can be present as dimer also. Okay. So they are extensively having hydrogen, intermolecular hydrogen bond, and this bond to break and go to the vapor phase, they require a little extra energy, or thus the boiling point is more than the other aldehydes, ketones and alcohols of comparable mass. What's the reason? Due to intermolecular hydrogen bonding. Okay. So next is simple aliphatic carboxylic acid up to 4 carbon atom are miscible in water. That means they are soluble in water. That is again due to the formation of hydrogen bond with water. But higher carboxylic acids are insoluble in water. Okay. Now the reason is increased hydrophobic interaction of the hydrocarbon part. Now for example, I have a carboxylic acid with a long chain of CH2 group like this, a very long chain. This is the hydrophobic part, correct? No, this is CH3, CH2, 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 a long chain is there. Okay. So what happens is, this is the hydrophobic part. As the hydrophobic part, that is the alkyl chain increases, they do not become soluble in water. Okay, so that is the reason that higher carboxylic acids are insoluble in water. Last is benzoic acid is the simplest aromatic carboxylic acid which is insoluble in cold water, and also carboxylic acids are soluble in less polar organic solvents like benzene, alcohol, chloroform, etc. Okay, so that's about the physical properties of carboxylic acids. Next, we are going to the chemical reactions. Under chemical reactions, first we will learn reactions involving cleavage of OH bond. That is, here you see R, C, double bond O, OH. So, first we are going to learn the reactions which is breaking this OH bond. Under that, first is acidity. Acidity of carboxylic acids. Carboxylic acid, when it is treated with electropositive metal like sodium, they can form the salt of the carboxylic acid, or sodium carboxylate ion is formed by liberating hydrogen gas. Also, carboxylic acid reacts with the bases to form again salt of a carboxylic acid and water. Also, it can liberate carbon dioxide gas from sodium bicarbonate solution, and this is used for testing the acidity of the carboxylic acid. You take a liquid, okay, and mix it with sodium bicarbonate. You can see the effervescence or carbon dioxide which is being liberated. So, this is again used for testing or detecting the carboxylic group. Okay, so that is the first part of acidity. Carboxylic acids can dissociate in water to give resonance stabilized carboxylate ion. That's why they can give away the H plus ions very easily, because if they give the H plus ion, then they will get the resonance stabilization. How we will understand here? See, for example, RCOOH with water. If this OH bond, hydrogen H plus ion is lost, that means the oxygen is taking up the electron of the hydrogen also. So this forms H3O plus ions, that is oxygen takes up the H plus ion to form H3O plus, and oxygen of the carboxyl group gets the negative charge. So this charge can become bond, and the bond can go as charge to the another oxygen atom. So you can see the negative charge, and here the double bond has come. Again the charge can form bond, bond can form charge, and there are two resonance structures which can be written as RCO with a dotted line and a negative charge like this. Okay, so due to this resonance stabilization, they can give that H plus ion very easily. And for the above reaction, we can also write the equilibrium constant because it's a reversible reaction. Okay, so the product H3O plus and RCOO minus divided by the molar concentration of the reactants H2O and RCOOH. H2O will take it on the other side. So equilibrium constant into molar concentration of water, we call it as Ka, which is the dissociation constant of the acid. So dissociation constant of acid is molar concentration of H plus ion or H3O plus ion into molar concentration of RCOO minus divided by molar concentration of the acid. Okay. Now, as I told you all, Ka is what? It is the dissociation constant of the acid. It is generally not told in terms of Ka value. We tell the acidity in terms of pKa value. And what is pKa? It is negative logarithm of Ka. All of this we have studied in the first PUC, isn't it? Now, smaller the value of pKa, stronger is the acid. So remember, they are inversely proportional. So if the pK value is less, that means this acid is very strong. So strong acids have pKa value less than 1. Moderately strong acids have pK value between 1 and 5, and weak acids have the pK value between 5 and 15. Extremely weak acid have the pK value greater than 15. So if the pK value is less than 1, it's a very strong acid. Between 1 and 5, it is moderate acid. Between 5 and 15, it is a weak acid. Extremely weak acid will have the pK value greater than 15. Okay, so that's about the acidity of carboxylic acids. Now we are going to compare this acidity That is, carboxylic acids have higher acidity compared to that of phenols. Okay, it's very important question. Carboxylic acids have acidity more than that of phenols. Why? What is the reason behind this? The reason behind this is the negative charge in the carboxylate ion is delocalized over two electronegative oxygen atoms. That is, you see R, C, double bond O and O minus. This is the carboxylate ion, correct? Now this will become, charge will become bond, bond will become charge. So you get R, C, O minus, double bond O, which again can come back to the same structure. So here there is a delocalization of electron between the two oxygen atom, which is electronegative. But in phenoxide ion, what will happen? In phenoxide ion, you have O minus. Again you have, it can come, charge can form bond, bond can form charge, yes. But then the delocalization is between oxygen and carbon atom, which is less effective. Okay, or I can tell, delocalization is less effective in phenoxide ion between one oxygen atom and less electronegative carbon atoms. Thus, carboxylic acid is more acidic than phenol. Okay, this is the reason. Next one, effect of substituents on the acidity of carboxylic acid. Now, carboxylic acid, always I wrote R, C, double bond O, O minus, and I wrote the resonance structures. Now, what is this R group? If the R group is electron withdrawing group, it pulls the electron, towards itself, or from the carbon atom if it is pulling, it stabilizes the carboxylate anion and the acidic strength increases. Always remember, if there is an electron withdrawing group, it pulls the electron away from the carbon atom or the carboxylate group. That means it is increasing the stability of the carboxyl group to give away H plus ion much easily, and thus the acidity increases. But if there is an electron donating group means it pushes the electron away from itself. So such group will decrease the acidity of the carboxylate group, and thus the acidic strength will decrease. So remember, electron withdrawing group, if it is present, the acidity will increase. Electron donating group, if it is present, acidity will decrease. Okay, thus the order of effects of group on increasing acidity is: phenyl group is least, then if the R group is iodine, bromine, chlorine, fluorine, CN, NO2, CF, all of this will increase the acidic strength of carboxylic acid. Thus, see here, CF3, 3 fluorine atoms are there, it is most acidic, then CCl3, then CHCl2, then CH2 with NO2 group, CH2 with CN group. So, like this you have the order of acidity of different carboxylic acids. Okay. So, if there is a vinyl group or a phenyl group which is attached to the carboxylic acid, then it will increase the acidity due to resonance effect. You can see, for example, this is the carboxylic acid group. For that you have the vinyl group which is attached, CH, CH2 double bond. So you can see here bond becomes one more bond, bond can go as charge. Okay. Similarly, the charge can come bond, bond can come as, bond again. So there is resonance stabilization which is there, due to which the acidity of carboxylic acid will increase. Okay. So this also you need to remember. Also, there is one more reason why the acidic strength is increasing in the presence of phenyl or the vinyl group. That is because the carboxyl group is attached to sp2 hybridized carbon atom. That's the reason the acidity is increasing. Now here if you see, we have electron donating group which is decreasing the acidity. pK value you can see. Here you have only one group which is pulling. So it is pK value is 4.19, and here you see electron withdrawing group is there, both. So the acidity is even less because pK value is less. Here the acidity is more, or I can tell pH value is less. Okay. So if there is an electron withdrawing group, acidity will increase. Electron donating group, acidity will decrease. Okay. So this you have to keep it in mind. Next class, we'll be learning about reactions involving cleavage of C and OH bond, that is carbon and OH bond, and reactions involving COOH group. So I hope you have understood today's class. Thank you, my dear children. Stay tuned, stay focused.